Hello everyone, welcome to our presentation. We are group 65. We have 3 members in our team. My name is Chao Chen. We also have Jingyuan and Wenhai. Our research topic is security in IoT. Let me briefly introduce our presentation outline. I will start introducing our research proposal and the motivations that drive us to do the research. Then put forward the main challenges. Afterwards, Jingyuan is going to elaborate several security patterns implemented in current IoT systems, such as ECC and symmetric key encryptions. The last part is about key management, which is one of significant security solutions adapted for the IoT context. The IoT is a network based on the internet, allowing all ordinary physical objects that can be independently addressed to achieve interconnection. The IoT has some security problems due to a large number of machines and lack of effective human monitoring. Therefore, addressing security issues in IoT is critical and urgent. Our research is conducted by searching relevant literature, comparing the advantages and drawbacks of different protocols and methodologies. The main security challenges in IoT include the following points. First, confidentiality. People want to ensure that their information is protected from anyone else, generally using access controls, permissions, and data encryptions to ensure the confidentiality. The second challenge is authenticity. Protecting the integrity of devices or data means that you are safeguarding those components from being modified or deleted by people who should not have access to them. Availability means that your systems are working properly in any time. The last challenge is key management. Loss of those keys can lead to loss of access to systems and data, as well as making a system completely unstable. Now I pass to Jingyuan to talk about security patterns.
There are several security patterns used in IoT to address the issues of confidentiality and authenticity, including public key encryption, lightweight cryptography, and symmetric key encryption. Only the first two patterns will be discussed in this video due to the time limitation. Elliptic curve cryptography is one currently used public key encryption in IoT. It has smaller key size and more efficient computation than other public key cryptography algorithms. Elliptic curves of the finite field FP and AC points within the field are the basis of ECC cryptography. The private keys are typically 256-bit integers that are in the range of the curved field size. The public key is an AC point and is the public point dotted with itself private key number of times. The triplet function is called the elliptic curve discrete logarithm function, which is a hard problem. An authentication protocol for secure communication between embedded devices and cloud servers through HTTP cookies was developed based on ECC in 2015. The protocol includes 3 phases. In the registration phase, the cloud server uses a one-way hash function taking secret key along with other parameters as inputs to compute the cookie for each embedded device. Then the cookie is transformed into an EC point and is stored on the device. In the pre-computation logging phase, the device calculates EC point P1 using a random number. Point P2 is calculated by applying a hash function to the random number and the cookie on the device. Point P1, P2, and the device ID are sent back to the server. In authentication phase, the server calculates the cookie of the device and then uses it to calculate P2 prime. The server then checks if P2 is equal to P2 prime. If they are equal, further mutual authentication would happen. Otherwise, the session would be terminated. However, Saru and 4 other researchers identified the vulnerability of this scheme regarding some types of attacks, and an advanced authentication scheme is proposed based on this one in 2018. Lightweight cryptography is also commonly applied in IoT since it is less complex and is suitable for many lower-resource devices such as battery-powered devices within IoT networks. SPEC is one lightweight block cipher and also an add-rotate XOR cipher, which means that its round function involves only 3 operations: modular addition, rotation with fixed rotation amounts, and XOR. SPEC supports a variety of block and key sizes. The number of rounds depends on both block and key size. SPEC is mainly used in software implementations to provide data confidentiality. SPEC has better throughput than some commonly used symmetric key encryption, such as AES and RC6 in GSM mode on IoT devices, according to a comparison study in 2019. Next, Wenhai will introduce key management solutions in IoT.
Thanks, Jingyuan, for introducing security patterns. Now it's time for me to talk about 2 key management solutions, which are certification authority scheme and software-defined networking with blockchain technology. Firstly, CA scheme is an approach establishing reliable end-to-end security services. The overall IoT network is divided into community-based subnets performing their own IoT policies. Transmissions between subnets relies on a dedicated object, which is a node with a high degree of resources and connectivity. These objects are certificate authorities in a higher level with certificate strings used. Furthermore, CA scheme has two variations, each has its own drawbacks. Centralized designs could have a bottleneck issue, while distributed design challenge community devices more. The design of IoT network has a high compatibility of heterogeneous community subnets. Independent protocols are supported, but each community should be responsible for their own devices. Another solution worth mentioning is SDN with blockchain. This structure introduces a mechanism of SDN controller to manage device behavior by updating their trust index for future arrangements. Certificates, trust index, and node histories are stored in a blockchain. This data are used for trust management and authentication, in which SDN controller will refuse requests from device with a small trust index. By implementing this solution, a flexible and scalable networking arrangements, as well as a dynamic trust and key management are achieved. Moreover, an additional SDN controller layer also releases the resources from individual key management. So in conclusions, we have introduced our research purpose and general methodologies, discussing 4 essential security challenges in IoT and explaining some security patterns as well as key management solutions. That's all for our presentation. Thank you.